Welcome to this channel once more as we look forward to generating new contents. If you are new here, please like, share and subscribe so that we enjoy this journey together. In today's video we are going to talk about machine learning. Machine learning is a subfield of artificial intelligence, AI, that focuses on the development of algorithms and models that enable computers to learn and make predictions or decisions without being explicitly programmed. It is based on the idea that computers can automatically learn and improve from experience and data. In traditional programming, a programmer writes explicit instructions for the computer to follow. However, in machine learning, the computer is trained to learn patterns and relationships from data, allowing it to make predictions or take actions based on that learned knowledge. There are several tools and libraries available for developing machine learning models. Here are some commonly used ones. Python is a popular programming language widely used in the machine learning community. It provides a rich ecosystem of libraries and frameworks for machine learning, including NumPy, a fundamental library for numerical computing in Python, which provides support for large, multi-dimensional arrays and mathematical functions. Pandas, a library for data manipulation and analysis, offering data structures like data frames that are useful for handling structured data. Scikit-learn, a comprehensive library for machine learning in Python, providing implementations of various algorithms for classification, regression, clustering, dimensionality reduction, and more. TensorFlow, an open-source library developed by Google for numerical computation and large-scale machine learning. It supports building and training deep neural networks. PyTorch, another popular deep learning library that provides dynamic computational graphs and an intuitive interface for building and training neural networks. R is a programming language and environment designed specifically for statistical computing and graphics. It has a wide range of packages for machine learning, such as Keras, a comprehensive package for training and evaluating various machine learning models, including pre-processing and feature selection techniques. MATLAB is a high-level programming language and environment widely used in scientific and engineering applications. It offers several machine learning toolboxes, such as Statistics and Machine Learning Toolbox, provides algorithms and tools for classification, regression, clustering, and dimensionality reduction. Deep Learning Toolbox offers pre-built and customizable deep learning models, including convolutional neural networks, CNNs, recurrent neural networks, RNNs, and more. Weka is a Java-based machine learning platform that provides a graphical user interface and a collection of machine learning algorithms. It is widely used for data preprocessing, classification, regression, clustering, and visualization. Microsoft Azure Machine Learning. Azure Machine Learning is a cloud-based platform that offers a wide range of tools and services for developing, training, and deploying machine learning models. It provides a visual interface for building models and supports various programming languages and frameworks. Google Cloud AI Platform. Google Cloud AI Platform is a cloud-based machine learning platform that allows you to develop, train, and deploy models at scale. It supports popular frameworks like TensorFlow and provides tools for distributed training and hyperparameter tuning. These are just a few examples of the tools available for developing machine learning models. The choice of tool depends on factors such as programming language preferences, the complexity of the problem, the size of the dataset, and the specific requirements of the project. It's important to explore and experiment with different tools to find the one that best suits your needs. The process of machine learning involves the following key components. Data, high quality and relevant data is essential for machine learning. The data serves as the foundation for training the model. It typically consists of input features and corresponding output labels or target values. For example, in a classification task to predict whether an email is spam or not, the input features could be the words and metadata of the email, and the labels would indicate whether it's spam or not. The data is divided into two main subsets. Training set. The training set is the portion of the data used to train the model. The model learns from this set by observing patterns and relationships between the input features and the corresponding labels. The size of the training set can vary depending on the complexity of the problem and the available resources. Test set. The test set is used to evaluate the performance of the trained model. It contains data that the model hasn't seen during training. By evaluating the model's predictions on this unseen data, we can assess its ability to generalize and make accurate predictions on new, unseen examples. The test set should be representative of the real-world data the model will encounter. Training. During the training phase, the machine learning model learns from the training data to make accurate predictions or decisions. The model's objective is to optimize its internal parameters or structure to minimize errors or maximize its performance on the given task. The process involves the following steps. Initialization. The model's parameters are initialized with random values or predefined values. These parameters control the behavior of the model, and their adjustment during training is what enables the model to learn. Forward propagation. The model takes the input features from the training data and processes them through its internal computations. It generates predictions or outputs based on its current parameter values. Loss calculation. The model compares its predictions to the actual labels or target values from the training data. This comparison is done using a loss function that quantifies the dissimilarity between the predicted and true values. Backpropagation. The model calculates the gradients of the loss function with respect to its parameters. These gradients represent the direction and magnitude of the parameter updates needed to minimize the loss. Parameter update. The model adjusts its parameters by taking steps proportional to the negative gradients. This update step aims to iteratively improve the model's predictions by minimizing the loss function. Iteration. The forward propagation, loss calculation, backpropagation, and parameter update steps are repeated for multiple iterations or epochs. Each iteration helps the model refine its internal parameters and improve its performance. Features. Features are the measurable properties or characteristics of the data that the machine learning algorithm uses to make predictions or decisions. Selecting relevant and informative features is crucial for the model's performance. Feature engineering is the process of selecting, transforming, or creating features to improve the model's ability to learn patterns from the data. Some common techniques for feature engineering include feature selection, choosing a subset of the available features that are most relevant to the prediction task. This helps reduce noise and unnecessary complexity in the model. Feature transformation, applying mathematical transformations to the features to make them more suitable for the learning algorithm. This can include scaling, normalization, or encoding categorical variables. Feature creation, generating new features from existing ones that capture additional information or patterns. For example, extracting temporal features from a timestamp or combining multiple features to create interaction terms. The choice and quality of features significantly impact the model's performance, and domain knowledge and intuition play a crucial role in feature engineering. Algorithms. Machine learning algorithms are mathematical models or procedures that define how the machine learning system learns from the data. Different algorithms are suited for different types of tasks. Here are some common types of machine learning algorithms. Supervised learning algorithms. These algorithms learn from labeled training data, where the input features are accompanied by the correct output labels. Examples include decision trees, random forests, support vector machines, SVM, and neural networks. Supervised learning is used for tasks such as classification, assigning labels to inputs, and regression, predicting continuous values. Unsupervised learning algorithms. These algorithms learn from unlabeled data without explicit output labels. They aim to find patterns, structures, or relationships in the data. Clustering algorithms, such as k-means and hierarchical clustering, group similar data points together. Dimensionality reduction techniques, such as principal component analysis, PCA, reduce the dimensionality of the data while preserving its important characteristics. Unsupervised learning is useful for tasks such as customer segmentation or anomaly detection. Reinforcement learning algorithms. These algorithms learn through interactions with an environment, where an agent takes actions to maximize cumulative rewards. The agent receives feedback in the form of rewards or punishments based on its actions. Reinforcement learning is used in areas such as robotics, game playing, and autonomous systems. Different algorithms have different strengths, weaknesses, and assumptions, and the choice of algorithm depends on the problem, available data, and desired outcomes. Evaluation. Once the model is trained, it needs to be evaluated on unseen data to assess its performance and generalization ability. This is done using the test set, which contains data that the model hasn't encountered during training. Evaluation metrics are used to measure the model's performance, depending on the task at hand. Classification. Metrics such as accuracy, precision, recall, F1 score, or area under the receiver operating characteristic, ROC, curve are commonly used for classification tasks. Regression. Mean squared error, MSE, mean absolute error, MAE, or R-squared are commonly used metrics to evaluate regression models. Clustering. Metrics like silhouette score or within cluster sum of squares WCSS can be used to evaluate the quality of clustering results. Evaluating the model on the test set provides insights into its performance and helps identify potential issues like overfitting, when the model performs well on the training data but poorly on new data, or underfitting, when the model fails to capture the underlying patterns in the data. If you find value in the content I provide, I kindly ask you to show your support by hitting the like button. Sharing the videos with your friends, family, and social networks would also be immensely helpful in reaching a wider audience. Lastly, if you haven't already, please consider subscribing to the channel to stay updated with all the exciting content